Okay, well, we usually start a couple of minutes late, but I'm going to say almost nothing for a couple of minutes. Just to remember, I'm Eric Feigelson, and I'm the coordinator of this class called Time Series Methods for Astronomy, which is being offered in spring semester 2017 at 3 universities, UNC, NCSU, and Duke University, through SAMC, this institute where we're visiting, where we're inhabiting right now. So I assume you know that. We are now a good way through the semester. Thank you very much, several of you, for providing your first homeworks. You can send your second homeworks to me as well. This class is pass-fail. But I think that will be it for the homeworks. And therefore, the next step is for you and I individually to discuss your project. And I sent you, I gave you an early, well, it's in the syllabus. I've got the syllabus here, by the way, if you want it. But I'm actually, as I mentioned last time, I'm flexible about the nature of the project. If you want to be more mathematical and less associated with data, it's okay. But any data you use has to be astronomical. I'll be glad to help you find it, guys. But I've no biology data allowed. No genes. Okay, out. Okay. I'd also like to say, in case there's any potential faculty in the room, that we have one slot open for a presentation on either March 29th or April 5th. And if necessary, I'll fill it in, but it is open for someone to present, or even 2 people to share it. So thank you very much. Okay, any other organizational questions from the students? Everyone okay? Okay. By the way, how many credits is this class? It's a 3-credit class.
I think so, right?
It's a 3-credit graduate seminar. Yeah, with real numbers in 3 universities. Yeah, SAMC is pretty incredible. Okay, very good. So now I'd just like to praise the fact that I'm no longer talking. But last time we had Ashish Mahabal, and today we have Eric Ford. And I don't know if you realize, but these are world-class senior scholars, and you're getting really unusual presentations here. And then we have a young scholar, also world-class, coming up next week named Becky Dawson. And then 3 of the people in the room are going to be presenting, the 3 postdocs who are here at SAMC. David, and Tuck will then present. And then we have spring break. Okay? So then one of your professors, Suman Lahiri, will present on March 22nd. During that time, I'm a little sorry. I'm not going to be present in this room. I have other responsibilities at Penn State and elsewhere for 5 weeks. So I will attend all of them through Rick's recordings after the fact. Okay. And if you have any problems, any of the presenters, what I just say to the postdocs, if there are any problems with the class while I'm gone, email me. I'm not gone in the sense I just disappeared off the earth. I'm just not resident at SAMC. So if you let me know, and any student who misses me, particularly I want to talk to you about your projects, and I will email you soon about that if you don't email me. Okay, that's it for the organization of the class. Thank you. Okay, Professor Eric Ford, Penn State, will talk about exoplanets, habitable worlds, and astrophysical modeling of exoplanetary time series, analysis of Doppler planetary surveys. The floor is yours.
Thank you, Eric. So a little bit of introduction. I'm an astronomer. I probably am a little more statistically literate than most astronomers, so I'll emphasize the astronomy and connections to statistics. I have more slides than we will do, I think 146. We do not need to get through half of those. I would much prefer to have a useful discussion of 25 of them than to have you all sit here and have me just talk for all of them. So please do speak up. And that's the carrot. And the stick is I got your name so I can call on people randomly if people aren't willing to volunteer questions when they see them. So a little bit of historical perspective about exoplanets, or planets around other stars, and really planetary science in general. So one of the exciting reasons that SAMC's having programs on astrophysics and exoplanets is that we're sort of in a golden age in terms of the science and the technical capabilities of astronomers. So if you rewind the clock a little bit, at one point in time, there was a geocentric model for the universe. So people model the motions of the planets in our solar system as going around the Earth. And then there was this, at the time, sort of controversial idea that maybe the planets went around the sun. And you could make models in which both reasonably fit the data that was available. And there was an argument made that the heliocentric model, where the planets go around the sun, was a simpler and more natural explanation for the universe. I would say that's basically a Bayesian argument, maybe Occam's razor, since Bayes wasn't around yet. But it's basically recognizing you can have multiple models that are consistent with the data and figuring out the best one. And we're going to have that theme as we look at other planetary systems, where we don't really know what's going on, but we can find the simplest possible explanation that's able to be consistent with our data and interpret that in terms of planets, masses, and orbits. So Galileo was an early astronomer, invented the telescope, or at least that's the traditional introduction for him. Made observations of things like the moons of Jupiter, which in some ways is like a little planetary system. Moons going around the planet Jupiter, observed their motion, recorded the data, and figured out their orbital periods, relationships, used it to do cool stuff like measure the speed of light. And in that case, he was able to directly see the dots of light that corresponded to the moons going around Jupiter. It would be lovely if we could do that for extrasolar planets. And occasionally we do. But the vast majority of exoplanets we see will not be detected by actually seeing the light from the exoplanet, but rather we're going to infer the planet based on more indirect methods. Now, indirect methods aren't foreign to our solar system. Back in the early days of astronomy, people plotted out the trajectories of the planets using the new heliocentric model, and recognized deviations between where the planets should be and where they were, and said, well, what could be going on? Either Newton's laws of motion are wrong, or there's something else perturbing the planets. And in the case of Uranus, William Herschel was able to pick out Uranus based on an observing campaign designed to find it. A very similar method was used to find Neptune. In practice, I would say they basically got lucky. It wasn't really that, it wasn't really due to perturbations from what we would now might call Pluto or the Kuiper Belt, but rather they sort of figured out where basically to look, and they had some erroneous data, but they at least were in the right general region. But the same method of figuring out how to search for planets was used for both Uranus and Neptune. So far, everything has taken about a century to make significant progress in finding one more planet. And so theorists, astronomers, made models and theories that evolved quite slowly, and they had lots of time to think about very detailed questions. Things like, why is the rotation period of Venus so long? This was, an important question in planetary science, and people put real serious effort into thinking about it. But they sort of took for granted that planetary systems would look like our own. They said, well, clearly giant planets form far away from the star, like Jupiter, Saturn, Uranus, and Neptune. And closer into the star, there's Venus, Mercury, Earth, and Mars. Rocky planets closer, and that's the way planet formation works. And so that was the prevailing wisdom for how everything would be. And that shaped what astronomers were willing to devote their efforts and telescope time to looking for. And in some ways, those theoretical notions slowed down progress in finding other planets because we were so focused on what we thought should be there, we didn't have an open mind and look for what might be there. As a result, in the early 90s, the first, I think, clear accepted discovery of an extrasolar planet was a really bizarre case of planets around a pulsar. So this is a star that was fairly massive. It went through its main sequence lifetime burning hydrogen to helium. It ran out of fuel. It underwent an explosion. It collapsed into a crazy state of matter that we'll never get to touch here on Earth. It's spinning really rapidly, blasting radio waves periodically, and serving as a clock. So the key thing is this pulsar is spinning around, and every now and then zapping you with radiation when its beam points at you. And because it's a humongous flywheel, that's an extremely steady clock, and we can look for very small deviations in when that little pulse of light or radio waves reaches us. And this way, Alex Wolskins, Dave Frail were able to detect deviations from what the pulsar should be doing and ascribe those to planets. An interesting sort of historical footnote is at the time, not everyone took this seriously because someone had very recently made a similar argument that turned out to be not due to planets, but rather due to a data analysis challenge. They erroneously inferred a planet when actually it was the Earth going around the sun. And so one common theme, many of us at some point or other analyzed our data and found a signal with a planet that's orbital period is 1 year. And then we go, wait a second, let me check my math. There's a bug in my code, right? So I've done it too, fortunately not quite as publicly. But so that history made people skeptical of this. And it was only through later being able to detect not only the planet's direct effect on the star, but also the planet's effect on each other that was sort of the conclusive proof that these really must be planets orbiting this pulsar. This may have been coincidence, or there may have been a little bit of causal encouragement, but other astronomers using a very different technique a few years later discovered what is sort of got the field really running fast. That was the first planet around a sun-like star, a main sequence star, still burning hydrogen to helium, emitting visible light that you can look up in the sky and see. And so that planet was detected by a relatively sort of modest observatory in the French Alps, not particularly big or high or great weather. But we'll see that instrumentation has played an important role in enabling the discovery of extrasolar planets. And this inspired other astronomers to start looking for planets. So this planet was surprising that it orbited its star very close to the star. It was so close to the star that a program designed to find binary stars could detect this planet. And so astronomers who had been trying to find lots and lots of binary stars and learn about binary stars found a planet. They got kind of excited. Other people said, well, wait, we could do that too. And we never bothered to check our data for planets with orbital periods so fast, so short. Let's go back to our old data, and what do you know? We had planets sitting on our disk that we never bothered to find because it was so unexpected that these planets would be here. A few years later, as the count sort of got up to maybe 20-ish or so extrasolar planets, the first case of multiple planets orbiting a sun-like star was discovered. And that's going to be the inspiration for much of this talk. That is, how do we interpret radio velocity or Doppler observations of stars when there are multiple planets or potentially multiple planets orbiting the star, and how do we make sense of those? So I think now might be a good time to sort of pause and see where people are, and so I need at least one question. Show me what you're thinking. Student question. Okay, we'll start. Debraj.
So in this planetary system, how many planets are there?
In this case, the announcement recognized, was it 2 or 3 actually? I guess it was initially 3. So they recognized one early on, and then after that they took more observation, later recognized there were 2 more. And now there's a somewhat debated claim of a 4th planet in this planetary system.
And are they rocky or they're gas giants?
In this case, all the planets are so massive that they're believed to be gas giants. Okay, good questions. Okay, glad to. From that I can tell that at least one person is understanding what I'm saying, which is a key piece of information.
What were the 2 telescopes? Like how big are they?
So the data came from both Lick observatories. This isn't the real this is Lick Observatory, but it's not the telescope that made the discovery. And then this is Whipple Observatory, where there was an instrument by the CFA group. In practice, my well, since I'm being recorded, I should be diplomatic. The quality of data from Lick was significantly better than the data quality from Whipple, but nevertheless, astronomers often have a rather collaborative spirit. They both sort of knew each other, been looking at it, and so they chose to combine their efforts and have a single publication that present both data sets, analyze them separately, and then analyze them jointly. So I mentioned it a little bit earlier that exoplanets is a bit of a tumultuous history in the sense of some of the first planets that were discovered way back when turned out to be erroneous interpretations. Basically, people doing poor statistics, seeing things, ascribing any little deviation what they expected to a planet, rather than understanding the noise characteristics of their data and being cautious. And so as a result, there was what's known as, I don't know, it was Latham's law or the first law of planet hunting, which is don't embarrass your fellow astronomers by announcing a planet. And so the people who did the Doppler planet searches were really paranoid. Basically, their strategy was take so much data that you don't need to do statistics, that it's just staring you in the face, and there's no doubt in your mind that this cannot be due to noise. And so, because it turned out there was a population of planets that was readily detectable by existing instruments, this was actually a viable strategy for a little while. It was just, when in doubt, take some more data. And that paranoia protected the field from gaining a dubious reputation, and in some ways was helpful. As time went on, some of the early astronomers start having students, and they start having students, and the sense of paranoia began to dwindle. And some people said, well, wait a second, why should we be so cautious? We should apply advanced statistical methodologies, and we should really dig into the noise to find evidence of planets. And some people started announcing planets that other people would then dispute, and in some cases, people would have a clear opinion, oh, there's one erroneous analysis. Other cases, they're basically dirty laundry in papers. Some cases, it's not just papers, but press releases. And once again, I think the field is beginning to get a little bit of a bad reputation because we haven't been able to maintain the high quality of reliability and reproducibility that we had in the early days when astronomers used paranoia as the defense against false alarms. And so one of the goals, I think, of astrostatistics is to take us to a regime where we can make strong planet detections reliably and reproducibly that everyone can agree upon without just taking way more data than we need. And that's going to require several pieces. It requires both understanding your data and modeling it well, and also sound statistical methodology. And so it's a benefit of sort of collaborations between astronomers and statisticians. All right, so the basic way this works is we have a telescope here. This is our cartoon telescope. We have a star here. The star has a planet orbiting around it, and the planet and the star spin around a common center of mass. And then as the planet goes around the center of mass, orbiting, say, at 1 astronomical unit, and the star, which is much heavier, orbits around that center of mass by an amount that's reduced by the mass ratio of the star to the planet. So in the case of the Earth, something like 3/10,000ths. We're able to measure the velocity of the star using the Doppler effect. So this is the, you hear an ambulance going by. When it goes by, you hear the frequency at a high frequency when it's coming towards you. As it's going away from you, the frequency drops. The same phenomenon occurs in light, except for the fact that the speed of light is so much faster than sound, you never notice it as a human being. But if you're an astronomer with a fancy detector, you detect that. So here's how we detect it. So the light from the star is split into many wavelengths using what's known as a spectrograph. And that starlight has imprinted on top of it dark absorption lines. So wavelengths of light where there's an atom in the atmosphere of the star, high above the star, that's absorbing starlight at a very specific wavelength. And as the star moves towards and away from the observer, the apparent wavelength of that absorption feature changes. And so we just need to measure the shifts of those absorption lines. Pretty easy. Problem is, this effect is very small. Remember, the speed of light is fast. A star we detect might basically be kind of walking speed, and yet we want to detect the shift of light due to that slow motion of the star. So the early discoveries, the 51 Pegasus, the first ones typically had velocities of nearly 100 meters per second. Now astronomers routinely claim to measure things with uncertainties of 1 meter per second and claim to find planets with amplitudes of a comparable amount. One of our goals in perhaps as little as 2 years would be to find Earth-mass planets. For Earth orbiting the Sun, the signature we need to see is about 13 centimeters per second. We're not there yet because of a combination of instrumental limitations, which will soon be overcome with a future generation of spectrographs, and because of statistical limitations in how to interpret spectra that are perturbed not just by the planet, but also by the star not being a perfect idealized sphere.
But there can be external noise too, right?
So there's measurement uncertainty that reflects how well your measurement measures what light was hitting your detector. But as I sort of mentioned, the star may not be a perfect idealized sphere. There may be astrophysics happening on the star's surface that previously was negligible or undetectable. But as we build better and better detectors, at some point, we can start to see the astrophysics of the star's surface having convections and pulsations and spots. And those things can affect the spectra and sometimes confuse us as to whether or not we're really seeing a Doppler effect due to the dynamical motion of the star or something going on the surface of the star.
When you look at the time series of this, could you actually, let's say for the non-noisy one and then for a really noisy one, would you actually be able to see it visually in the time series?
Indeed. I'll skip to that and I'll come back
Or
to
is it something that you have to look at, like the periodogram or something?
Yeah, so here's a case where we have a relatively typical time series, where on the x-axis we have time in years here, and on the vertical axis we have velocity. And you can kind of see, well, there's maybe some measurement uncertainty associated with each point, and it's not clear there's anything beyond that. So this would be a typical non-detection. So if you went to the telescope and you observed 20 stars, 19 of them would look like this.
What's the blue line?
That's just, I don't know. Probably in some previous version of the slide, this was on 0, but with scalings and things, it moved. Basically, a flat line, so no change in the star's velocity is sort of your model of no star of the planet. But then in other cases, you see a much more interesting pattern. But if it's okay, I'll come back to interpreting that pattern. I'd like to say a little bit more of the data collection process, because astronomers work pretty hard at this. And so the first step in finding planets is really building an instrument that's capable of measuring these small things. And it's a little bit useful to think about how this works in practice. So you have starlight that's magically collected from a telescope into a thin little beam, and you bounce it off a bunch of optics. And the purpose of those optics is to spread out the starlight. And what you have as a detector is sort of a typical CC detector like in your smartphone camera. And so we need to take that starlight and instead of having it be one really long time series, wrap it onto a detector of reasonable size. So you have to build a fancy instrument to do that, go to a telescope to collect the data. Many of these time series represent the efforts of some graduate student or postdoc going to the telescope for 100 nights a year for many years, being replaced by another graduate student collecting the data. So some of these data sets represent a lot of astronomical work. I have a very minimal role, I think like 4 nights at the telescope or something, just enough to sort of learn what it's like, but there's some people who really specialize in the process of collecting the data. And so once they do that, the data they get for every observation that's taken is a starlight split into a spectrum that looks like this. So at the top left, you'd have infrared light. At the bottom right, you have light that's in the blue, maybe even in the ultraviolet. And then as we go across each row here, the wavelength goes from red to blue, kind of wraps around, red to blue again. And then each row is a bigger jump in wavelength. And of course, in real life, it's black and white. You don't have the color coding. But from this, you can see certain prominent features here, which are actually the combination of many, many spectral lines. And so if there's a Doppler shift due to a planet, the line should shift. The only problem is the amplitude of the shifts that we're now measuring correspond to the width of a single silicon atom. So it's not so easy to see the shift in those cases. So let's say we have a data set where we've collected a bunch of radial velocity observations over many years, and you can pretty easily see the data is not consistent with a constant velocity. So something's going on. Now from this, can anybody sort of read off any properties of the planet?
2 years.
2 years. So I'm guessing you kind of picked maybe two peaks like this, take their distance, and what do you know? Bam, 2 years distance. Very good. You passed Astronomy 101 here. So, 2.2 years. 10% I'll give you. The other key thing that you maybe can't quite read off in terms of physical parameters, but the other key property you can get out of this would be the overall level of the signal. Right? So we can measure how large are the velocity variations. And from that, we can then convert the amplitude of velocity variations we observe, taking into account the orbital period. We can use Kepler's laws to relate the orbital period to the orbital separation, and then infer a planet mass. Now I put up here minimum planet mass. Why do you think this mass might not be the real mass, but rather just a minimum planet mass?
What are the dotted lines?
That's my model, so I fit a model to it and just draw it to guide your eye. So we're measuring what? The velocity of the star. Now, could we tell if that star was moving in the plane of the sky? Since we're relying on the Doppler effect, at least in the classical limit of slow velocities, the Doppler effect is related to the velocity towards the observer or away from the observer. And so if the star is coming towards you, you notice. If the star is going left and right, you won't notice it. And so there's a geometric factor, sort of the orbital inclination of the planet projected either you're in the plane of the orbit, in which case you see the full effect, or you're perpendicular to the plane, you see no Doppler effect. And of course, most of the planetary systems are somewhere in the middle, where you get some projection of the velocity along your line of sight, but not the entire effect.
And do people know what that angle is?
Sometimes we might get lucky and actually see the planet pass in front of the star, in which case we'd know that it must be very nearly edge-on. That's the most common way, but of course most planets don't pass in front of their host star for any single observer. Occasionally we have extra information. For example, if they're interacting planets, we might be able to measure the strength of the interactions as a way to measure that inclination. But again, that's a small fraction of the planets that are found this way. So in most cases, we only have this amplitude and a minimum mass based on that amplitude, and we'd have to answer questions like how common are planets of a certain mass in a somewhat statistical population sense. Yep.
So is it the eccentricity of the orbit that gives sort of like that shape in the velocities, like the slower rise and the quicker fall?
Yeah, very good. So you notice that this wasn't a sinusoid, which you might expect if the planet was traveling on a circle, but rather the velocity of the star goes towards you, and then, it goes slowly towards you. No, I was right the first time. It goes quickly towards you, negative that Doppler effect, and then slowly away from you. And so what's happening here is the orbit is an ellipse, and that Kepler's third law, the orbit is sweeping on equal area and equal time. So as it comes in close, it whips around, and then as it goes further away, it moves more slowly, and then it comes back in, it moves more quickly. And so as a result, we can get either a skewness in this case, or you can also get sort of like one peak being broader than the other peak, depending upon how the orbit is oriented. And so deviations from circularity are sort of noted initially as sort of a first harmonic, some power at a frequency twice that of the fundamental mode. And then in extreme cases like this, with an eccentricity of 2/3, you can just see it by eye, and it causes significant distortions to the shape. So that's the third sort of key piece we can sort of read off of the properties of this planet from these Doppler data sets. Someone sort of alluded to this. One problem is, so I showed you a planet with an orbital period of 2 years. And so we took data, say once a month for several years, you could sort of see the pattern very easily. But what if there's a planet whose orbital period is significantly shorter than the time between when you observe? Maybe you go to the telescope once every month, and the orbital period of the planet is 4 days. Well, then it's kind of like a random variable. Where was the planet at the time you went to the telescope? And you get something like this. You can sort of tell there's an amplitude, but you can't tell if it's just crummy data with noise or if there's a pattern, unless you are willing to try looking and basically testing a whole bunch of possible orbital periods. And so one tool that astronomers often use is known as a periodogram. The sort of basic form that's commonly referred to as astronomers, the Lohm-Scargill periodogram. Basically what this involves is fitting a sinusoid to the data and saying, I will consider many different orbital periods. At each orbital period, I'll fix the period, but I'll allow the phase and the amplitude to be unknown parameters. I'll find the best fit orbit conditioned on a certain period, and then I'll report something like either chi-squared or this. People use this power that's kind of a crazy statistic that has terrible properties, but basically some statistic that tells you how good of a fit is a model with this orbital period. And then one of the more controversial or historically troublesome aspects of the periodogram has been figuring out how big a peak do I need. Here's a peak at 2.6 days, and there's a lot of power. There's a relatively good fit. If I phase that data at 2.6 days, how big does that peak need to be for it to be statistically significant? And the challenge is that in making this periodogram, I may have tried tens of thousands of possible orbital periods and found the best one. And so the best one's always pretty good, right? Like you can just choose a really fast period that goes up and down really fast and fits all the data pretty well. When is that significant? And so some of the early papers that used analytic expressions for the false alarm probabilities are problematic. And so if people don't calibrate these using Monte Carlo simulations, you should be suspicious.
They're also not false alarm.
Yeah, so as Tom will point out, the language is misleading. The statistics used made assumptions that weren't true. So in many ways, there were problems. And hence, this astronomers' version of just be paranoid and make sure this peak is really, really big was sort of their approach to having confidence in these detections. So if you find a period that looks pretty good based on a periodogram, then you can take your data and instead of plotting it versus time, plot it versus orbital phase, or sort of time divided by the orbital period, modulo 1, or if you want to work in 2 pi or 360 degrees or whatever, but sort of the time since a given epoch modulo the orbital period, and that orbital phase that implied, you can see that same data set I showed you previously that looked like a bunch of noise, well now there's a nice clear sinusoidal pattern. And so in this case, there's a planet with an orbital period of 2.6 days, an amplitude of about 20 meters per second. And this is, again, a pretty strong detection. Now, in the old days, one of the advantages of the periodogram was that it was fast. You could show that the computation time required to compute a periodogram scaled as n log n, where n was the number of frequencies you tested. And testing 50,000 frequencies, that was important. These days, computing power is so cheap that's kind of irrelevant. So people sometimes do procedures that involve testing lots of periods, which don't have any of the properties of the original periodogram of, say, scaling as n log n. They still call them periodograms. I think that's misleading and whatever, but you'll see it in the literature. As people call basically anything where they try a bunch of periods and report a goodness of fitness a periodogram, even if it's not, say, the original Lohm-Scargill periodogram, if it doesn't have the key properties that made it useful back in those days.
I have a question about it. I'm not very familiar really with using periodograms. Are you looking for like one period? Like here you picked out that one. But what if you had like a couple that were significant?
Yeah, so that's going to be the focus of this talk in some sense is what do we do if there could be more than one period? So in this case, we went through the list and said, let's try one period at a time. We assume a single sinusoid with a single phase, period, and amplitude. Try it. Try the next period. Try the next period. Just go through a long list of them, find the best one, and go, let's plot up. Woohoo, this one looks good. And if there's only one planet that you can detect, that works quite well. The challenge becomes, what if there's 5 planets around the star, 3 of which give you large signals, and 2 of which are near the threshold of detection? What do you do with that? And so we'll see that's a bigger challenge. So one way in which this time series problem may differ from a lot of other time series, say like in economics or type things, is we actually have a physical model for what's going on. Planets are following Newton's laws of motion going around the star. So you don't really have to worry about every variable. Basically, it is saying that Newton's law of gravity and Newton's laws of motion can be equated to get the path that planets take following good old-fashioned Newtonian gravity. It's a set of differential equations. If you have position in 3 dimensions, velocity in 3 dimensions, you have 6 differential equations per planet to solve. You solve them, you now have the motion. And it's, you can do that in milliseconds, typically, for most planetary systems.
What are the RIs?
That would be, say, the position of each planet, so the strength of the gravity. Oftentimes, the orbits of the planet can basically be assumed to be independent of each other. So each planet is going around the star, but any interactions between the planets are so small or take so long to be noticed that you can approximate each planet as just orbiting the star. And the star's motion is a linear superposition of the signal due to one planet and the signal due to the other planet. And so a very common assumption to deal with this problem you asked about, what if there's multiple planets, is we'll write an expression that's, maybe I'll call it semi-analytic, for each planet and take a linear sum of them. The one thing that makes this expression annoying is that there's a transcendental equation that's to be solved at each time of your observation to relate the time of your observation to where the planet is on its orbit, sometimes known as the Kepler equation. So we typically solve this with an iterative solver. 4 iterations is normally just fine. Oftentimes 2 or 3 iterations is just fine, but nevertheless it's slightly annoying. And so if you profile your code to do this, you'll find that a lot of the time is spent solving Kepler's equations. It makes 80% of your time on an efficient code. And this expression can work well when we have planets, even if they're on highly eccentric orbits, as long as any interactions are either so weak or so slow that they're not detectable in your data set. There's another approximation that can be useful, and that is sometimes the orbits of the planet are sufficiently close to circular that it can be useful to fit circular models. And indeed, that's basically what the periodogram was. We said, let's assume the planet's traveling on a circular path, so it signals a sinusoid. Well, now we can compute stuff more efficiently than solving Kepler's equation. And several parameters become linear that otherwise are nonlinear, so you can use, you don't have to use an iterative root solver for finding the best fit at a given period. So in this case here, we'd be summing over the effect of a few harmonics. In many cases, 0, 1, or 2 harmonics are basically all you can detect, given the limits of your observational precision, and then summing over potentially different planets, I. And so that's the challenge. So before I showed you a couple of cases, here's the original 51 Pegasi, now with a little bit better data, nice, really whopping signal. Here's a case where we have another massive planet. Instead of being highly skewed, now that's sort of like a narrow peak and a broad valley, another signature of an eccentric system. Here's a case where we have a really long period planet that's eccentric with a fast rise and slow fall. Then here's a case where the pattern doesn't exactly repeat. And what's that a sign of? And we don't have the same pattern repeating over and over again. Well, maybe 2 planets, right? So in most cases, we intentionally target stars that are either single stars or at least so far away from another binary star that we can cleanly separate the light so that our telescope is observing 1 star at a time, because interpreting the data from 2 stars is often hard. So we typically choose stars that are either single or just such wide binaries that basically you can treat as 1 at a time. So in principle, it might be a brown dwarf or another object, but in these cases, the amplitude's small enough that these perturbations would be due to 2 planets. So the thing that sort of got me interested into exoplanet statistics was I was looking at some of the discoveries that had been made, and they had things like a reported best fit orbit and error bars that I show here, what the observers reported their measurement precision is. And one thing that might be a little bit disturbing is that the error bar went to negative eccentricities, so that means that probably their approximation wasn't so great. But then the other thing that really bothered me was they updated their web page, and they took some more data, and they updated the orbit. And the best fit model went from here, with a nice little error bar of just that one, all the way out to here. I'm like, well, wait a second, that should never happen, right? It's that the odds that your point moves by, I don't know, 10 sigmas, this is in log scale even, so that's 100 sigmas, right? It's just ridiculously small. So something's not right here. And so I'm like, can you like look at that again? They say, oh yeah, sure, no problem. We've taken some more data. We've updated. Don't worry, it's a lot closer now. But of course, my reaction was, no, we were even more, right? Clearly, our ability to characterize the orbital properties wasn't working so well. And so what this illustrated was that the statistical methods people were using at the time were underestimating the uncertainties in the orbital properties, in some cases quite dramatically. And so I set out, how can we do better? So maybe now I'll walk you through, first I guess why that happened. And basically what happened was we had a very long period orbit. So instead of seeing the same thing happen over and over again, we had basically just seen 1-ish orbits. But was it 0.8 orbits? Or was it 1.2 orbits? Or was it 0.1 orbits, right? Because the pattern hadn't quite repeated yet, it wasn't really clear that it was repeating. And so for these long period planets are particularly susceptible to these challenges. So how do we quantify the uncertainties in the orbits of extrasolar planets? And so I'll sort of walk you through a few methods that have been used. Originally, a common method was to use the Fisher information matrix, basically describing the second derivatives of your log likelihood at the location of your best fit. Pretty soon, astronomers started recognizing that wasn't quite right. They would use bootstrap methods, where they generated synthetic data sets and analyzed those. That still has some issues, and then later we'll talk about using Markov chain Monte Carlo as a method to characterize those. So Fisher information matrices, is that something that people here are familiar with, or something that I should go over? And astronomers, this would be something I'd have to explain, but maybe here, can we raise hands if we want me to skip things? There's no what? Oh, I can't spell Fisher. It's confusing because there's statistician Fisher and there's astronomer Fisher who spell their name, I think, differently.
Observed Fisher.
Fair enough. So the basic idea is we approximate the chi-squared surface as quadratic, and then you use that as a description of the log likelihood or log target density. Obviously, this is very fast and easy. The problem is if your actual log target is not described by a quadratic, then you have a problem. And so if we look at typical chi-squared surfaces where I've picked one parameter out of, say, 5 or 6, a very common scenario is that we have lots of little short scale wiggles and then a much broader trough surrounding it. And if you were to find your best fit model here, 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 each one of them has a very sort of narrow valley, but the different valleys are separated by more than the width of individual valleys. So one issue that the classic Fisher information method has is that it doesn't recognize the broader chi-squared surface. Another problem that particularly shows up for these long period planets is that in some cases it's not well approximately a quadratic, there's an asymmetry. If I've observed the star for 5 years and I say it hasn't gone around the star yet, I'm very confident it hasn't gone around the star multiple times, but I'm not so sure, well, is it going to come back around in 6 years, 7 years, 8 years, 10 years? And so my chi-squared rises much more gradually at longer periods. And so in some cases, maybe it's sharp enough that I can still measure things well. In other cases, maybe it's so broad, I basically haven't measured the period yet. And so one thing we now encourage the astronomers to do is to pay attention to how that chi-squared surface varies for long periods.
On the left plot, is that an actual exoplanet case?
That's a synthetic exoplanet data set where I knew the answer in the back of the book.
But is X period? Or what?
Yeah, there's its orbital period. So in a bootstrap method, maybe not be the formal statistics bootstrap, but it's sort of the same spirit of resampling. Astronomers basically say, let's imagine data sets we might have collected. And there are different ways you can do this. You could say, I believe I understand my measurement uncertainties, and so I'll add extra noise to my data. This isn't quite right because your data already has one set of noise and you add more noise. So now it's noisier than before. Another thing they might do is they might try to fit the best model they can, get some residuals, and maybe scramble those residuals. That can be good if your measurements aren't particularly well characterized what their uncertainties are. It assumes that things are uncorrelated from one observation to another. So if you have correlated measurement errors or uncertainties, then the scrambling method can sort of hide things from you. So there are issues with it, but basically it allows you to get around problems like this because the little peaks often move around in this resampling. But it typically fails miserably at this because every time you draw a curve to the same feature of a sharp rise at smaller period but a slow rise at long period, and as you generate different data sets, it doesn't change that. And so if you only report how much the minimum moves around, you still don't capture the fact that long period orbits can be excluded.
Is there a sense of how many observations you would need before bootstrapping is reliable?
Typically, there are some planets in the literature with as few as 12 radial velocity measurements. Those are typically very large signals, and I wouldn't trust the bootstrap uncertainties from those. More typically, there's probably a couple of dozen observations for a radial velocity planet with large amplitude. For small amplitudes, it might get to 100 observations per planet. I think you're exactly right that the assumptions of the bootstrap are not met.
It's not. This is not a trivial problem. The way you outlined it is the way astronomers do it, and that's just not a correct bootstrap procedure, period. It's just not even done, not even formulated correctly as a bootstrap confidence interval problem. It's actually very tricky to do the bootstrap this way. This is essentially the parametric bootstrap for a nonlinear model to get a joint confidence region. That's basically an unsolved problem.
Yeah, so as I mentioned, it's not the exact statistician's bootstrap. It's sort of in practice what astronomers do. It's better than, I'd say, just a classic Fisher information test, but I think the primary point I made was this method was failing us, and so we needed to do better.
Where does the chi-square come from?
So this would be comparing the velocity you measured each time to the prediction of your model. So in the case of, say, a circular planet, it would be coming with the best fit sinusoid to your data and looking at the sum of the squared residuals to that model.
Oh, okay.
Good. Yeah, sorry, I should have said that sooner. So this motivated us to consider Bayesian approaches to characterizing exoplanet orbits. And from the philosophical side, the main benefit is we're actually able to answer questions we want to ask as opposed to answer questions we don't care about. And it allows us to actually do things in a principled way. I think for this audience, maybe it's not so important. One thing I will emphasize is that it sort of forces you to be explicit about your assumptions. And sometimes this is just a annoying section in your paper that takes up space, but sometimes this is important because you didn't realize what assumptions you were making and hence why you were concluding things that maybe you shouldn't have. So I think one benefit is that if you force yourself to write down your assumptions, sometimes you realize that they weren't quite as innocent as you might have assumed. Now, of course, the big problem with Bayesian methods historically has been that it requires computing lots of integrals. And there was a time when doing those integrals was impractical. Particularly if you had a complex model, you had many model parameters, and so this was really what held Bayesian methods back even through, say, the 80s or early 90s. And so the thing that sort of took Bayesian methods from a sort of curiosity among statisticians to something that was applied widely in astronomy was the adoption of Markov chain Monte Carlo methods into the toolbox of astronomers. So are people familiar with MCMC, sort of the principles of that and how it works? I see a few nods, some holding out. Okay. So this will give us a sample from a posterior distribution for the target posterior distribution in our case, and each step of our Markov chain is fast compared to, say, doing a minimization problem, and this can be an efficient way to sample from high-dimensional parameter spaces. And so this gives us results that, we have some disadvantages, yes. In principle, if you run it infinitely long, it gives you the correct answer. In practice, you never run it infinitely long and you have to worry. Could the fact that there's correlations between the successive steps mean that I should be cautious about interpreting the outputs of my Markov chains in terms of science? So we need to pay attention to that, but that's probably a different lecture than this one. So sort of outputs of these analyses. So here each row is one radial velocity data set, and the main parameters we extract: the orbital period, the amplitude, the eccentricity, and something about the orientation of the orbit. In each case, I show two curves, one computed via Markov chain Monte Carlo, and one computed based on the Exoplanet astronomer's version of a bootstrap. And you can see in some cases they match so nicely you barely notice there's two curves. Everything's, I don't know, it doesn't really matter. I can figure it out. The one that gives you bigger errors is the MCMC. The one that gives you smaller errors is the bootstrap typically. So.
The one that can have two bumps must be the MCMC.
Well, no, you can get two bumps with bootstrap type approaches. So you can see here, for example, this broad tail, that's a property of the MCMC finding long period solutions, whereas the bootstrap was fooled into only choosing small periods. So the solid line is the MCMC, the dashed one would be the bootstrap. So you can see that sometimes they give similar results, that's sort of encouraging, but in other cases they give quite different results. And so that was one of the things that got us started in switching the exoplanet community from using frequentist approaches to Bayesian analyses of their Doppler datasets. The good thing is this wasn't very computationally expensive. You could do this on sort of one computer under a desk. It might take a few hours. You didn't have to think very hard. You could use the sort of most basic MCMC algorithm. Okay, there were a few parameters to tune, but just kind of looping over them and sort of figuring it out. One naive graduate student could do this for many planetary systems. And here's for the astronomers the introduction to standard MCMC techniques. The challenge with MCMC techniques is that in some cases, when you have a target distribution that's non-trivial, if you choose everything well, maybe your chain mixes well like this one, but in other cases, maybe you take a whole bunch of steps barely moving, rejecting every proposal, and only occasionally get to move around. It's big jumps. The alternative is you take lots of very small steps, but then you can have long correlations in your Markov chain. So this can be problematic. And so the traditional thing to do is to try to choose a proposal distribution that captured the shape of your target posterior so as to be efficient. And over a decade ago here at SAMC, I worked with some statisticians to figure out how to design better MCMC samplers to make this efficient so that we could solve more complex problems. So these are the challenges we just mentioned. Convergence can be slow. Another issue is that the methods we were using, the Markov chain Monte Carlo, meant every step depended upon the previous step. And so parallelizing this was problematic because you could only parallelize as much as you could parallelize one model evaluation. And about the same time, people outside of computer science were realizing computers weren't speeding up anymore. So I mean, when I was a graduate student, it was totally routine. You would write code that was really annoyingly slow, and whether you were company or science, you wouldn't care because in a year, computers would be so much faster. You would just buy a new computer, and then your really slow code would be a fast code. And they just got so much faster. This worked. Eventually, though, the limitations of dissipating heat on your microchip meant that computers didn't get faster. What they did get is they got more throughput by becoming more parallel, so you still could do more work, but it had to be parallel work. Now, Intel and compilers are very clever, so they work to sort of hide that from you, so some of the parallelism could be done behind the scenes by the compiler and the microchip, but fundamentally there is this problem, and this problem persists today in the sense of if we want to have algorithms that are able to get the benefits of highly parallel computer chips, then the standard Markov chain Monte Carlo algorithm requires parallelizing our model, which could be very hard to do and often is not worth the effort because it would take so much effort. Whereas if we had a statistical algorithm that was intrinsically parallel, so we could just give each worker, each CPU or GPU core, a different set of model parameters to evaluate, it would be trivially parallel with minimal communications cost and allow us to take advantage of the increasing power of computer chips. And we recently bought a nice new computer cluster, so I went by and compared the cost. Back in 2004, the number one computer on the type of the ones that were publicly admitted, maybe the NSA or something had a better one, what was less powerful than a single graphics card that you can buy for $3,000 today. And indeed, you can even get consumer grade ones, not quite data center quality, for a few $100s. And so what used to be tens of millions and a large room with high-speed infrastructure now fits in a workstation under a grad student's desk. They kind of buy it with their own change. And of course, if you buy a cluster of these, you have orders of magnitude more computing power than was possible even for the most impressive non-classified operations just a little bit more than a decade ago, but we need a way to harness that power. And so the traditional MCMC method couldn't take advantage of this, and basically still be running at the same speed as we were a decade ago. And so this motivated the use of what I'll call population or ensemble MCMC methods that instead of evaluating each model individually, consider an ensemble or population of model parameters and compute a Markov chain over that population. So typically we will use language of sort of genetics like generations, and we'll evolve each generation of parameter states. Now if you're a statistician, you may go, wait a second, what are you really computing the posterior of? You now have a high dimensional space. Technically, our Markov chain is now over a product space of all the different models we're comparing. So we're doing 1,000 models at once. We're computing a Markov chain over 1,000 times the number of dimensions per model. Very high dimensional, and you can worry about convergence issues, and it's sort of interesting in its own right. But in practice, we're able to efficiently sample from that parameter space much more efficiently. So we're able to do two things. One is harness the increasing parallelism of computers becoming available, and the other is we're able to automatically generate good proposal distributions without having to be an astronomer who thinks very carefully about the particular data set and details of that planetary system like we did in the past. So there's two methods that are pretty common in astronomy. One is known as differential evolution MCMC. The other is known as affine invariant ensemble MCMC. Have people heard of either of these or used either of these? Would it be useful to describe sort of these algorithms? Okay, good. So both algorithms are capable of automatically figuring out what shape and scale of proposals to try to work efficiently, and can be tuned by just one or two parameters. So instead of having to tune maybe a covariance matrix with n squared over 2 parameters if you have an n-dimensional problem, now we just have 1 or 2 parameters to tune, which also dramatically simplifies the operation. First, let's consider the affine invariant sampler. We have a population of model parameters in some here 2-dimensional state. Each point here represents a set of model parameters. We want to update this generation, so we go through and say, let's pick one model that we want to update, color it blue. Then we say, let's pick another one, here green and J, and we'll draw a vector between the two. That's our proposed displacement, direction at least. We'll scale it by some factor. The way you choose the factor has to meet certain theoretical properties to preserve the detailed balance of the Markov chain so that you get a sample from the distribution you want to get a sample from. So then you generate this scale factor, and did I lose? Oh yeah, so that's your proposal. And then just as before, you accept or reject the proposed state, and in this way we're able to generate proposals that know about the shape of the ensemble. So if the ensemble is basically scattered uniformly, it's guessing in all directions. If it were highly correlated, the proposals would know about that high degree of correlation, and that's how we're able to increase the efficiency in high dimensions. This is basically for the well, I was thinking this would be the slides people could refer to online if they wanted to, say, implement their own, but since we have statisticians, the change in the acceptance probability, we now have this factor 1 over z, and here's sort of a function that affects the scaling relation here, one particular choice of that. And so here we have one parameter a that affects the tuning of this algorithm.
Is it somehow related to Gibbs sampler?
I don't see a connection. So what we're doing here is we're perturbing every dimension of the model at the same time. But instead of saying, let's propose something centered on where I am now with a sort of fixed distribution, we're saying, let's generate proposals by considering 2 points and their relationship, which is to propose something in between them. And in some cases, the scale factor can go in the opposite direction. And so we're making use of the information contained in your present estimate of the posterior shape to propose trials that have a higher probability of being accepted than if we did, say, a random walk MCMC.
So the blue dots in the previous, like this represents something you believe about the shape right now.
Well, the sort of overall distribution of shapes would be the present generation of the sampler. So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, about 10-ish sets of models in our current generation. And by drawing random pairs, we're drawing displacement vectors that know about the arrangement of those 10 models in parameter space. The differential evolution algorithm is basically the same idea. The only difference is we'll pick 3 points, we'll generate 1 to update, and 2 to generate a displacement vector 2, and then apply it to the third one. Same basic idea. Using the knowledge you have about the present, about the shape of the distribution from the Markov chain's current distribution generation in order to make proposals that are more likely to be accepted than would otherwise.
Is it also affine invariant?
It might be. That's not something I can tell you off the top of my head. Actually, I believe it is. So what are the comparisons between these? Basically, they solve the same problem the same way. The main difference is that this algorithm is a little bit more exploratory. The previous was a little bit more exploitative. And so if you are guessing an initial set of parameter values that aren't close to the true posterior mode, this algorithm will be able to recover more rapidly. Whereas if you have a sample that's already from the posterior mode as your initial population, the affine invariant one will be a few tens of % more efficient in proposing trials than the differential evolution MCMC will.
Why is that again?
So you can sort of see that this method can propose. Imagine I had a distribution instead of being, say, a single Gaussian mode, had 2 bumps. Well, and also, imagine I had 2 modes here. I had samples from both, right? Well, with the affine invariant one, it would do things like choose things halfway in the middle, which are probably terrible. But in this one, there's a chance you draw 2 points from the same mode, so as to explore that mode. And there's also a chance you draw 2 points from opposite modes and enable a jump between them.
So there's actually a step you didn't mention, which is to not multiply by.
There's a scaling factor here, sorry, just as before.
So you can only successfully jump between modes if, like, every 10th step you don't include that factor. But no, I was trying to understand when you said that the affine one is faster if you're like in a unimodal situation.
If you're in the
because it's more,
if you're in the unimodal case and you already have a posterior sample from the true posterior, its acceptance rates might be 10, 20% higher than of the differential evolution, at least in the sort of experiments that I did sort of as part of a summer school a while ago. Again, mostly for your reference if you want to implement this on your own. The algorithms are actually really simple. You can implement them in, I don't know, less than 12 lines of code, I'm sure. The one thing that's a bit of an art, as Tom alluded to, was how do we choose the scale factor? As we go to higher and higher dimensions, we generally want to have smaller and smaller scale factors. So to say explore 1 mode. But if we have multiple modes we want to jump between, we occasionally need a scale factor very near 1 to allow us to jump between the 2 modes. So doing something where you occasionally take a big step or propose a step with a scale factor near 1, but typically try something with a scale factor that's reduced to account for your dimension is a good strategy. And that's where the one sort of artistic aspect of the differential evolution method. The other aspect that both of these suffer from is they evolve a population of initial states. What's your initial population? So if you give it a sample from the posterior, it evolves that sample from the posterior very well. Very good. But if you start with a sample that's not from the posterior because you don't know what it is, how do they perform? And so some of the tests we had early on was how robust are these algorithms to initial guesses that aren't near the posterior mode but have to move a bit away. Of course, if you create a mean enough posterior that has a big spike in the middle, they'll never get over that barrier, and you're guaranteed to be wrong. If you have realistic sort of, well, if you choose to analyze data, once your data is good enough that the truth is sort of evident in the data, then hopefully your posterior isn't so annoying. So we do want to do tests to make sure that things like how long we run the algorithm are chosen to solve simulated cases and work robustly to plausible poor guesses for the initial sample. So basically what we do is we simulate a planetary system. We imagine what if we guess its period wrong by a certain amount? How long would it take my Markov chain to recover? And then we sort of run our real Markov chains twice as long to make sure that if we were that far off, they would have had a chance.
And actually use the periodogram to initialize one.
Yes, right. So we generate our initial guess of the period based on the periodogram, but we know that because of the aliasing and mobile planets, we could be off potentially by kind of use our astronomical intuition what we think the error bar likely is, and so we then use that to guide our initial guesses.
When the initial population is off, has it been compared to how fast it converges to that versus traditional MCMC?
I haven't compared it to traditional MCMC. What I have looked at is how long does it take it to converge to the target posterior. So somewhere, let's see if I can make this movie go. How do I? My mouse is, oh, here we go. So here's a case where the true posterior mode is over here. And I mean, I do a really bad job, right? I intentionally start at like 5 sigma away over here, really annoyingly bad, and give it a small width and say, what will it take? And of course, the first thing it does, it says, I'm nowhere close, and it spreads out really big. And then with time, some of them start to find the true mode, and they start to bring in. One of the problems with the differential evolution or the affine variant is that if there's one point out in Timbuktu, it's very hard for that one point to get a proposal that brings it back to the true posterior mode. And so you'll see the vast majority of samples find this posterior mode pretty quickly, but the time required for these last ones of drifting can be really long. So in practice, what we do is we let them burst over, 80% of them very quickly find the mode, and then after a while we say, you know what, if your log target density is 10 to the 10 worse than the sort of bulk of the points, let's just throw you out and restart with that. So maybe the mathematicians won't like it, but it's a lot faster than waiting for these points out here to gradually random walk into.
Each of the points are still going in succession, right?
Yeah, so each.
Not like happening all at once.
Not happening all. So each frame of this movie, every point has been replaced by a trial that was accepted or a repeat of itself. And
that's how you're like using the parallelization as the idea.
Right, and so the parallel, I mean, yeah, of course you can just serialize the algorithm, but because every every model evaluation of the proposals is independent of the other model evaluations. If you have a population of 1,000 sort of walkers or particles in your simulation, you can parallelize over 1,000 processors with basically 100% efficiency.
So the original papers suggested you use small populations.
Yes.
Do you find do you use larger populations because of the speed up from the parallelization, or is there actually value just from numbers of iterations for doing the larger population?
So as in standard MCMC, if everything was serialized and you had a choice between running one chain 100 times as long as some reference length or 100 chains of equal length, then the running one chain 100 times long in theory should be better. The benefit of dividing up a few is if something bad happens, you're more likely to notice if you run a few of them. And well, maybe running 5 or 10 typically would be all we would do to sort of test to make sure they all do basically the same thing. And we wouldn't split that up, say, 1,000 different ways. Same thing with these. If we have, say, 100 walkers, then, or I guess the choice is how many walkers we make. If we have, say, 10 dimensions, then we probably want at least 20, 30 walkers to characterize the covariance of that distribution. The benefit of adding a 40th or 300th or 3000th particle doesn't improve the algorithm's efficiency. And in some sense is worse because our Markov chain isn't as long as if we had fewer particles longer. But if we're not serializing the algorithm, if we're actually running it in parallel, then it may be that it costs us just as much computer time to run it with 1,000 particles as with 10 particles. In which case, we do get more posterior samples by running with more particles.
So it was worth noticing on here in terms of, I realize you didn't do the comparison with some standard Metropolis Hastings, but Metropolis Hastings would have kept the proposal size fixed, and it would have had to random walk all the way to the true posterior.
Indeed. So the differential evolution can capture both the shape of the proposals and the scale. And so that scale isn't constant, nor the shape. So when you first start out, the shape and scale are based on whatever you chose for initial population. But then as it starts to evolve, it may say, I'm off in a region that's distribution is kind of tilted this way, things start to stretch out this way, the proposals get bigger and bigger in that direction, and then once they sort of get close, then they start to shrink again. And so one benefit is that throughout the simulation, the proposals evolve from the burn-in stage to the stage you would hopefully only use, the only part you would use for inference would be after it had found the posterior. But during that process, it sort of automatically can update its scale. And so the great thing about this is if I have a planetary system that's kind of complicated, an observing schedule, and maybe I add some special type of observation I don't always have, instead of having to think about what does my posterior look like in 21 dimensions and choosing proposals that know about that, I can basically say, run and see what happens. And so this made it much more easy on the humans running them. And so represented a very nice advance in terms of the human effort involved in analyzing them. Did I skip over something to go reach here? Someone asked, I think that's a good question that caused me to go here, but now for some reason my computer is totally confused where I am. Aha, very good. Okay, so what can go wrong is always an important thing to consider when using an algorithm, because anything that can go wrong will. One issue we talked about is making sure our initial population was close enough to the target density the algorithm could converge in the true distribution. So a good thing to do is to simulate data, make informed and poor guesses, and test that they're still able to find the true target density in that case. Another possibility is I mentioned that this algorithm is fairly robust. There being strong correlations between parameters. If they're literally linear correlations, that's true. You can have very strong correlations, and it does just fine. But instead of having nice elongated ellipsoids, you start to have bananas and sickles and crazy nonlinear type of correlations. Then, just as before, your step proposals need to sort of shrink in order to have a decent acceptance probability. And so that can result in long autocorrelation times. And as you get to higher dimensional spaces, it's sort of increasingly likely that some pair of dimensions will have some funny nonlinear relationship. So it's you don't need to worry about sort of, say, doing a PCA analysis on your parameters to orthogonalize them. But if you know about nonlinear transformations that would make your parameters you're proposing, your target more linear in that reparameterized space, that can still be highly advantageous. And
Could I ask you a question?
Sure.
First of all, just how many parameters are there per planet?
So in radial velocity, you typically have 5 parameters per planet if there's no interactions, and 7 if there are.
Okay. So there's actually without a slide, there's a famous controversial system called GL581. And everyone agrees there's 4 planets. But the big question is there 5 or 6? I think it's the 5th one or something. If it's there, it looks exactly like Earth. So there's a whole lot of interest in, now it's just really great. So let's say 5 planets, 5 parameters, 25-dimensional space. And the question of that 5th planet is it a 20-dimensional space and it has a perfectly nice peak? Or is it a 25-dimensional space that has a slightly better peak? So do you have first of all, did I phrase it in a crude way, right? And could you phrase it better? And also, could you say, how does the algorithm help you on that one?
So
It's not the only problem people have,
right.
but it's a famous problem.
So the famous case Eric mentioned of GJ581, the papers that have addressed it have traditionally asked the question, is a, say, 4-planet model, 5-planet, 6-planet model significantly better than the other one? But the real problem with them is not so much that they did that comparison poorly or something. It is that the assumption was it must be one of these models. There must be 0, 1, 2, 3, 4, 5, 6 planets, and there's no other possibility. And as they went to lower and lower mass and planets with smaller signals, stellar astrophysics became detectable. And so the real question is not, should I model my data with 4, 5, or 6 sinusoids? The question is, should I model my data with 4 sinusoids plus stellar activity, or 6 sinusoids and no stellar activity? And how do I weigh those two? And so, unfortunately, astronomers still don't have a first principles model of stellar activity to put in. If they did, it would be very expensive. So there is the question of doing the model comparison properly, which at least some papers struggled with. But the real issue is, in that case, the stellar activity problem. So I'm going to talk about, after the break, how we would compare models of different dimensions, different numbers of planets, to assess the Bayesian evidence for 1, 2, 3, 4, 5 planets, assuming that we have a set of models which is complete. And so the problem with, not the problem, but anytime you do statistical analysis, if you consider a finite set of models and choose between them, but the reality is none of the above, what is the consequence of working within a misspecified model? So that's a long-standing problem. So I think now, I did have slides to illustrate the problem of a linear correlation that differential evolution would do well with, a nonlinear correlation it would struggle with, choosing the sample size, making sure it runs long enough. The final possibility was multiple modes. We sort of talked about this earlier. If there's sort of two modes that are close enough that or you just know about them in advance, so you can start some samples in both modes, this can work reasonably well. But if there's 20 modes, right, then the odds that you choose an update that takes you from one mode to the other start becoming ridiculously small. And so the traditional DMCMC algorithm really struggles. There is a variant that's able to do quite well, and that makes use of parallel tempering. For some reason, the basic idea with parallel tempering is that instead of sampling from a single target density that may have multiple modes that are widely separated, like say maybe these purple ones here, the blue ones here, where there's the density goes very small. What if instead I take my target density and I raise it to some power, less than 1, so as I flatten out my density? So now the valley between these two peaks is not nearly as extreme, and so maybe I can have a Markov chain that is able to go back and forth between the modes. And then if instead of just doing the case of point beta of 0.1, if I have a set of Markov chains, each with a different beta, and I can propose jumping from a sample from the purple target density to a sample from the cyan one, and from the cyan to the red, and the red from the green, and the green to the blue, I can have a way that a walker from this mode can get over to this mode by going up to high temperatures, across from one mode to another high temperature, and back down. And so if computing were expensive, this of course would be very painful. But if you have a GPU that has thousands of processors anyway, well, why not have 100 chains at 10 different temperatures and allow them to swap back and forth? And you can use parallel tempering as a way to solve the problem of multimodality. In principle, just as before we had the challenge of technically our target density was an outer product of n particles times n dimensions, so a lot of dimensions. Now our target density is not one density, it's the outer product of the density at each of these temperatures. And so for our Markov chain to converge, it can't just converge at the lowest temperature. Our Markov chain also needs to converge at the high temperatures. And you need a way of assessing whether or not every one of those temperatures has converged and is well mixed and so the problem I find with this is not running it. Running it runs very well. It's just making sure that I'm happy with the output is kind of a challenge. So maybe someone who really needed this might be able to automate that a little better. So at the moment, running this isn't hard, but I don't know of anyone who's really automated the detection challenge. I think that's probably.
Could I just ask?
Oh, yeah.
There's a famous British code that claims to be designed well for this multimodal problem. This, 10 bumps that are very separate. It's called multinest. Do you have could you describe it? Have an opinion?
So multinest is a completely different approach to sampling from posterior exterior. So it's akin to a sequential importance sampler where you make multiple estimates of the target density and try to evolve them in a certain way so as to converge upon your true target. If you give it just like in MCMC, if you start with a target density that's from the posterior and evolve it, it does very well. If you are able to start with an importance sampler that has that knows about your target distribution, it will do quite well. But whether or not it will converge upon the true density is not obvious. I think would be one way to say it. The MCMC algorithms have this proof that if you run them long enough, infinitely long, they will converge to the true answer. Now, maybe to a mathematician this is really attractive. I can prove it works. To a practitioner, maybe, I don't know. To a mathematician, a multi-nest algorithm that may or may not work because it's just a heuristic approach that seems to do well on some data sets may be very unsatisfying. To a practitioner who says, I'm analyzing the C and B data just like a bunch of people before me and it's always worked well for my colleagues, they may be happy with that trade-off. One thing that I'm not happy with is if people use an algorithm without validating that it works well for their problem. And so the people who study cosmological models where multi-nest has been compared to Markov chain methods and they see that it converges reliably when they run it over and over again, I think that's a fairly responsible use of multi-nest. When people say, I'm going to go search for a certain type of planet in a data set where we've never tried using multi-nest before and just assume that it finds the target posterior without doing any tests, I think is a bit dangerous. It probably does pretty well most of the time, but unless you've done tests that your algorithm works on something close to your problem, you're basically hoping. So that's my biggest beef with some of the multi-nest applications. I don't know, Tom?
It would be a good thing for a statistician to look at it, because there isn't really any good theory behind it, and it is fairly popular. Not sure it's there might be a time series example that could be worked on. If you wanted to make it a class project or something, but it does seem to me to be an algorithm kind of crying out for a theorist, somebody with a theoretical bent to take a look at it.
I think Christian Robert has looked at it a little bit.
Not multi-nest, he's looked at nested sampling.
Oh, okay.
Nested sampling is a sound approach. It's like Metropolis Hastings. It's a meta-algorithm, right? There's lots of things you have to set in it to make it a real algorithm. So Christian looked at the simplest version of nested sampling and found that it wasn't really competitive. At best, it did as well as on his test problems as other common MCMC approaches. Multi-nest is inspired by nested sampling. It aspires to be nested sampling. I'm not sure that it is. That's the issue, is whether it's really a sound version of nested sampling.
And the tuning of it is quite heuristic, so whether or not it's...
Well, thank you, because Eric and Tom are giving you substantive comments. I'm going to give you a non-substantive comment, a sociological comment. Those two methods, affine invariant, MCMC, and multi-nest, by far have taken over astronomy. Each have dozens, if not hundreds, of papers per year, and with a strong, weird correlation as to which continent you're on. If you're in America, you use the one from New York City, and if you're in Europe, you use the one from Cambridge. Okay, so please,
it's interesting that
this is not the way things should be done,
So that statisticians know about both of them. The affine one was published in the statistics literature, and as you said, Christian Robert, nested sampling was published first in the Valencia Proceedings, and it's been studied. And nobody in statistics uses either of these algorithms.
Right.
They're known, but they're ignored. So
the astronomers are doing two advanced, specific advanced things hundreds of times for extremely important studies, including multi-planet studies, and all of precision cosmology, and many other problems. And
differential evolution does get used in some other places, but not the affine invariant.
The evaluation of the appropriateness of a given method for a given problem is almost always absent.
I think what's really sold these are that there are easy-to-use codes written by astronomers, so the APIs are in a style that's appealing to astronomers.
It's entirely
that's not a good reason.
It's entirely sociological.
So I'll editorialize on that a bit. So when I was starting, I remember my advisor said, well, you have a choice. You can either make your tool easy to use and make it public available, and lots of people will use it and you'll get lots of citations. Or you can treat it as, your secret sauce and not tell anybody how to use it, and try to extract all the value you can out of it. I did something in the middle. I described the secret sauce in complete detail so anyone who wanted to could have used it, but I didn't make the code public, partially because I had used some numerical recipes as copyright, it's kind of a pain, but partially because I thought, you know what, if I make it really easy to use, people who don't understand it will use it, and then they'll do stupid stuff and people will blame me. So I think in some sense I was right. People who implemented it generally had to understand it. In some cases, they did publish things that had errors because they didn't quite follow my instructions. And later, we figured it out through emails and things. But for the most part, because there's that barrier of writing at 8 lines of code, that was enough to make people understand it and for the most part use it responsibly. On the other hand, people who say that the MC algorithm made a nice little Python package where you can install and it makes pretty little plots or whatever, people use it a lot. They got way more citations than I did, not just in exoplanets. The problem is people often use it irresponsibly and do stupid stuff. And so in some of the science collaborations and partnerships I've been a part of, my biggest contribution was basically saying, I don't think your Markov chains have converged. Let me see those. Look, you're nowhere close. Go back and run it longer before you even send me a draft of your paper, right? And basically, people, because it was so easy, they did silly stuff without understanding what they were doing. And if they hadn't had me as a co-author or collaborator, they would have published total junk. Not even wrong. Just like things that were highly dependent upon their initial guess, in no way related to solving the problem they were trying to solve. So which is better? I don't know, right? It's not like one was clearly the right choice. Clearly more people have done good science by the thing that's easy to use. They're mixed in with the things that sort of were irresponsible uses. And so I think this highlights the importance of educating astronomers about statistics, because it's not just, some of these are literally 8 lines of code. They're not that hard. But you do have to, understand what you're doing. And sometimes people in their rush to be productive gloss over the understanding. And so I think that's why things like this astrophysics course and SAMC and educational efforts like Eric and Jogesh work on are so valuable, because they're not just providing a black box and say run, but trying to provide the foundation on which people can build. And so with that, maybe we'll take a break. Welcome back. So I've sort of talked about the histories, a little bit of the motivation, and what the statistical methods we use, and now I want to show some applications and sort of how it works in practice. So remember we discussed that in the simple case of planets orbiting a star without any interactions, we could view it as a linear superposition of each planet interacting with the star individually. But in some cases, there's a planetary system where the planets were interacting so strongly and so quickly that we could detect the interactions of the planets with each other. So in one sense, this is a pain, because now your model evaluation is orders of magnitude more expensive. On the other hand, it's an opportunity, because now we can measure things we couldn't measure otherwise. And so I'll pick a few of the classic systems that have been observed so long and so well that we can detect these variations and learn things about those systems. So in some sense, the likelihood is unchanged. It's basically a chi-square distribution comparing your model to your observations. The thing that's changed is we've replaced this linear superposition model with an integration of 6 n first order ordinary differential equations if we have n planets. And so this isn't that hard. I mean, this might take milliseconds or tens of milliseconds, but if we end up doing this billions of times, that can add up. And so, oh no, I don't understand what's so the first thing that we did, and I mentioned this mainly because I want to encourage other people to do it, is when you try to solve a hard problem, don't just jump to analyzing the real data, but first analyze a hard problem that's similar to your hard problem where you know the answer in the back of the book. Because then you can tell if you failed miserably, and you can do something about it, and you can learn from how you fail and say, oh, well, the reason it failed was this, and I could change something. And so that learning process, sometimes it takes time. You don't always get much credit for it, but at the end of the day, I think it's an important thing to do, and I wish we could convince our field to be a little bit better about first demonstrating the validity of your algorithms on simulated data sets. So the first thing we do is basically test how much burn-in was required for these algorithms to work on these hard data sets. And then we use that to make sure we burn in long enough. So here's a data set, radial velocity observations of a star 55 Cancri. It's a bright star. You can literally go and see it with your own eye in the sky if you know which one to look at. People have observed this over 1,000 times going back to the 80s. So in the old days, each observation was very expensive and they only got a little bit of telescope time. You can see in here, people started just finding planets around other stars. They got more telescope time to observe things more intensely. They could tell they found a planet. They reverted to observing it occasionally. Hey, wait a second. Our one planet model isn't good enough. Let's start observing more intensely. This is about when they found 3 planets. Then we convinced them to sort of keep observing and lots of observations. Different colors coming from different telescopes. Different groups got involved. Detector upgrades, all sorts of complications. So now we have a relatively rich data, or a very rich data set. This is one of the few most intensely observed Doppler stars at high precision. The basic sketch for what we have is 5 planets. There's the first planet that was detected was 55 Cancri b, because astronomers name things in important ways. So this is an analog to hot Jupiter, a giant planet with a short orbital period. Later on they found C. So the orbital period is about roughly 3 times the first planet. And that was scientifically interesting. Is that just a coincidence? Or is there actually some physics that cause their orbital periods to line up in a commensurability that has implications for planet formation? Then they noticed there's this long period trend, and so they invoked planet D. And this is interesting because it's a very long orbital period. The only reason we're able to detect it is we've observed this star so long, and it's in many ways our best analog to Jupiter. Actually like Jupiter with an orbital period of over a decade. Then they noticed a very short period planet. In this case, a super-Earth, a planet of radius about 2 Earth radii and comparable in density to that of the Earth. And then there was a claim of a planet sort of in the middle. This one basically is uninteresting, like in all the cool ways. Other than to do the inference problem properly, you have to include it. So it's mostly a nuisance. So we wanted to analyze this data set, and previously, people would analyze these 2 planets. Then they would sort of fix these 2 and analyze this one. And they would kind of like fix those and analyze this one. They sort of do these ad hoc methods, and there was no self-consistent dynamical and statistical analysis. They would sort of fix one thing at a time. And so what we wanted to be able to do was to analyze the whole system. So we could ask questions like, are planets B and C actually in a resonance associated with this 3-to-1 orbital coincidentally? How circular or eccentric was the orbit of the outer giant planet? And what is the mass of this super-Earth after we account for all these interesting effects and planetary interactions? So what do we have? In the non-interacting model, we have 5 model parameters per planet that describe the planetary system. In the interacting model, there's 7 parameters per planet. There's a few that you can rotate along the line of sight, so you can remove one, and you can add a few because detector upgrades and things, but sort of order of magnitude. In the non-interacting model, each model evaluation is fast, so this might be something like tens of milliseconds. The interacting model is quite slow because we have to integrate this set of differential equations, and that inner planet that goes around the star every 2 days, we have to resolve that inner planet's orbit, and we have to do it over 2 decades. And so this now is quite substantive. And so we had to combine the clever algorithms with significant computational abilities. The output of our month-long GPU integration is this high-dimensional posterior. In each little postage stamp, you can see the shape of the correlated parameters. And if I pick one of the most interesting little pairs and blow it up, you can see here I compare the orbital period of planet B and planet C. And I can see the target, or the posterior density, is clearly not 3.
What's the parameter count when you're in this regime? Like, is it still 5 parameters per planet, or can you get more because of interaction?
Because the interactions were able to constrain the mutual inclinations between the planets. So in the traditional case where the sign I is unknown, in practice, the strongly interacting planets we can measure the mutually forward, the weakly interacting ones we can't. So we either have to have some parameters that are really poorly constrained, I can't find them here, or we sort of leave and we hold them fixed and say this parameter doesn't matter to speed things up. But sort of order 30-ish, 40-ish model parameters depending upon how paranoid we are. So of course, one immediate problem you can recognize is when you get this output, what do you do with it, right? So you have to sort of bring your science questions to the data and then pick out, I want to look at particular parameters of interest. And so one of the things we're interested in this case is this observation just from the first papers that the orbital period of these two planets was nearly 3 to 1. So one's about 15 days, the other's about 45 days. And so there's a theory where when planets form, if they're interacting with a gas disk, the gas from which they formed, their orbital periods can change and they could get trapped in certain resonance configurations where they start moving together due to torques in the gas disk and back reactions on planets and stuff. So people for a while had assumed that they're so close to 3, they're probably in this resonance. What we showed was actually the orbital periods differ from 3 by about 1%. At the time, that was sort of new and novel. Now we've subsequently found lots of other planetary systems where orbital periods differ by a few percent. And we actually find that it's actually fairly common for planetary systems to be close to, but not near exact resonances, and are trying to understand the implications of that for their planet formation history. But in order for the system to remain stable, the two orbits do have to interact in a way that allows them to avoid the system becoming unstable. So say planets colliding or getting kicked out to float in space or falling into the star. And so that condition requiring them to be stable means that these two orbits are elliptical, where they have sort of a direction where their closest approach is. And if they spin independently of each other, sometimes the two planets will come close to each other and bad stuff will happen. But if instead the two orbits basically track each other, and they sort of know which way to point, then they can never come so close that there's a dynamical instability. And so when we take the posterior distribution for the model parameters and integrate those systems forward in time for tens of thousands of years, we can then characterize how closely those two angles track each other. And we can see that they do indeed typically librate with a relatively large amplitude, but nevertheless avoiding configurations that would lead to close encounters.
If you fit a system with just multiple Keplerians, is there a simple criterion that tells you, oh, you should have been using n-body?
Well,
you have to compare, you have to just see if the residuals don't look white, you have to actually compare it to n-body?
So there's sort of two ways n-body matters. One is if I took the best fit orbit I got, or the posterior I got, and I integrated them for 100 million years, would that system be stable? And in most cases, the uncertainties in the true parameters are so broad that there are acceptable solutions to your data that are not plausible because the system would self-destruct in a million years. And the odds that we're seeing it right before it self-destructs are basically 0, right? So typically we add the extra constraint of assuming long-term stability. How does that further restrict our information about the orbital parameters? But in a case like this where you have 1,400 observations over 2 decades, you can actually measure the posterior well enough that you can integrate the solutions forward in time and see, A, the system actually, should be stable, and B, look at that long-term evolution. And that's because we are detecting the mutual interactions. Now, in a case like this, the mutual interactions, basically, you can't see them by eye. There's another case, GJ876. Right, in the residuals, you wouldn't notice them, right? In other planetary systems, you actually can see them by eye. And so if I get around to showing GJ876, you can look at those and sort of see there's a certain beat pattern that's due to the precession of the orbits. In that case, the elliptical nature of the orbit is causing each planet's orbit to spin around once every 9 years. And so if you observe the system for 2 decades, you see it spin around twice. And you can see the radial velocity curve sort of changing shape as that orbit spins around.
So for roughly how many systems have people done in-body calculations?
Well, we've done n-body calculations for dozens of radial velocity systems, most of the time imposing the dynamical stability constraint to answer questions like, what are the constraints in the mutual, remember those sin I factors? This was the minimum mass. Well, we'll get maximum masses, assuming stability, and then we'll also get information about how nearly coplanar they'd need to be.
So this wasn't doing in the context of MCMC, it was like an a posteriori analysis?
Well, in those cases, we typically run MCMC assuming a non-interacting model, and then we do a dynamical analysis. That basically is good enough, but of course, being someone who values statistics computing, we say, hey, we have a fancy hammer. We could compute the interactions as we tilt the system closer and closer to face on, the masses of the planets get bigger. And so for the same orbital periods, at some point, when it's very nearly face-on, the masses are so big that interactions become detectable. And so we'll do these sorts of MCMC on-interacting planet models to get the mass constraints for systems as they become sufficiently inclined, their masses become big enough that we could detect the residuals. So if you ask the question, how many planetary systems could n-body integrations for is there an inclination that without n-body integrations you wouldn't exclude? Well, then it's dozens. But most of them aren't at 80 degrees or something, right? And so, or 10 degrees inclination. So in terms of we actually detect interactions for the system, it's probably less than 10. But they get all the attention because they're the interesting ones. Right, so then other things that we can do is we can compare the measurements of the mass we get out for the super Earth mass planet here. Basically it's 8 masses, the density derived, compare it to the density of Earth, and see that indeed this is a planet that has the density of rock. Now maybe molten surface, but it's not, for example, a big ball of ice or it has a large hydrogen atmosphere. So actually learning about the composition of planets sort of indirectly thanks to dynamical analyses. And then perhaps the last fascinating system about this is that outer planet, whose orbital period is 13 years, a little bit longer than that of Jupiter, traditionally measuring their orbital eccentricities at long distances, you typically find fairly eccentric giant planets. And this one, interestingly, has a very nearly circular orbit, only a few % eccentricity. And so on one hand, somehow this system got planets close in. Maybe that involves some violent formation processes. But on the other hand, this outer giant planet somehow managed to maintain a very nearly circular orbit. So there's an interesting constraint on the formation history of this planet, and sort of planet formation theorists get excited by things like that.
How big is planet B?
It's it's 8 Earth masses. Okay, so in this case, I told you up front there were 5 planets. But I want to sort of go back to the question we had earlier for maybe a couple of places, which is, well, how do you know how many planets there are? And could you add another one? And this really comes back to what does it mean to discover a planet? And so this is sort of both philosophical and practical complication. So in the old days, the way we discovered a planet was we rejected the null hypothesis that there were no planets. And we assumed the only thing that would cause a star to move was planets. And so if we rejected no planets, then there must be planets. The simplest model is 1 planet, so we found a planet. Okay, that was useful for a while. The Bayesian approach is based on evaluating the evidence, and I capitalize it because that is a specific technical meaning, that the model with a planet is greater than the viable alternative models. And it might be the n+1 model is greater than the n planet model, but we also need to keep in mind there might be alternative models that aren't just planets, so particular worrying about stellar activity.
So that's what statisticians call a marginal likelihood.
Yes, evidence are marginal likelihoods. So before we sort of go off on talking about the Bayesian method, well, why did the frequentist method work reasonably well for so long? And perhaps the first issue is just the planet amplitudes were big enough that you could get away being a little bit not using the full statistical information. But the other key part was the stellar activity that was needed to explain the radial velocity variations would have been so big that it would have had other easily observable consequences. So if you have a 100 meter per second signal that's all due to the star pulsating, well then the star's brightness will change noticeably, and so you would notice it. So we could sort of reject the stellar activity as causing 100 meter per second variations by extra information about the brightness of the star. As we sort of get more precise and we start to measure 3 meter per second, 1 meter per second, maybe tenths of a meter per second precision, now the stellar activity needed to mimic that Doppler shift is so small that we're not sure if we can recognize it. And so David Jones may later tell you about some of the things they've been doing to try to find a way to recognize this activity. But that's still very much work in progress. Another thing that's interesting is astronomers in the early days really valued finding planets, so they would design their survey to find planets. They would do things like pick single stars, and pick stars that were close in properties to the sun, but maybe had a few more metals which previous observations had hinted might be correlated with finding planets. They would design their whole search to make it so they could find lots of planets. And they prioritized having a good track record so that their group had a good reputation over claiming low significance planets. As time went on, going from 10 observations to 20 observations is annoying, but you can do it. Going from 20 observations to 40 observations is twice as expensive. But once you've collected 1,400 observations, just saying, oh, well, let's just collect another 1,400 observations to be sure, that's not a viable option, right? So at some point, the idea of, oh, just collect a little more data, you're collecting lots of data to try to detect these Earth-like planets already. So you can't just sort of rely on the hammer of more observations to collect more data when we have a change. So as we've shifted to try to find smaller and smaller planets, it's important that we be able to make detections that are closer to the threshold of sensitivity without just throwing oodles of telescope time at it. And here you can sort of see the progress of the Doppler method. This is the velocity amplitude of the planet as a function of the year that people published the discoveries. And you can see that with time they got more and more confident. And then basically somewhere in here it sort of plateaued around mostly 2 meters per second. There's a few people who dared to dig in the noise, and we can argue about whether that was wise or not wise. But sort of the rapid improvement in velocity now has basically stalled for almost a decade. And that's not because of the measurements not improving, it's because the stars they're targeting have astrophysics that has amplitudes potentially comparable to a meter per second. And so that's been a real thorn in people's side. Okay, so statistically, we'd like to calculate the marginalized likelihood. In a sense, it's pretty simple. You just integrate over the prior and evaluate the likelihood, add it all up, no problem. But this is actually a problem, because everything I've told you so far has relied on Markov chain Monte Carlo to draw samples from this posterior distribution. And the good thing about Markov chain Monte Carlo is you can decide whether or not to accept or reject a trial by taking a ratio of the target probability densities. So I never actually needed to know the denominator of this marginalized likelihood. So I've never actually computed this thing, which actually appears in Bayes' theorem, because we've cleverly chosen an algorithm that makes use of a ratio where it cancels out. So now I say I want to use that. So we need to calculate, but we have a posterior sample, but not an actual estimate of the integral itself. And if we want to compare two models, then the Bayes factor would be the ratio of the marginalized likelihood for those two models. So here's the integral we'd like to do. There's been a lot of proposals in the literature of ways to try to estimate this integral from a posterior sample from an algorithm like Markov chain Monte Carlo. The SAMC a decade ago, several of us tried about 10 of these methods, and about 8 of them had such poor convergence methods, the result was we should never use these, at least for our problem. So basically you have very high variance estimators, and even worse, they look pretty good for a while, and after the 10 millionth iteration, bam, that result just changed by orders of magnitude, and you run it for a few more tens of millions iterations, it starts a little less converged, and bam, it jumps up again. So a lot of the methods that we were exploring were extremely large variance estimators and very problematic. So we set out to try to find something that was practical. And so one possibility is to use importance sampling, where basically you multiply and divide the denominator by the same distribution. Now you sample from your importance sampling density G, you evaluate some ratio, and compute that integral. And since since you're able to draw from this distribution, you no longer have that problem at the denominator, and you can just compute the ratio, and we're all good again. The challenge with this, well, there are a few challenges. One is choosing a good just distribution G. So maybe if you have a nice target density that's nice and nearly Gaussian, you can choose a G pretty well by looking at your posterior sample. Even then, the danger is if you run it for a long time to get a good estimate, and you occasionally get something where G is 10 to the minus 9, well, you have this 10 to the minus 9 in the denominator. And so even with importance sampling, we found it still had a larger variance estimator than we would have liked. So when we use this method, sort of transfer it to a finite sample size, we still had some annoying properties. And so the method that I'll describe today is actually a special case of a generalized version that we developed in the last AMC. Jim Berger was the one who originally suggested, as far as I know, where basically what we do is we take this distribution G, but instead of drawing samples from the full distribution, we truncate it. So we say, well, we're not going to draw things out in the tails distribution. We're going to focus where there's significant posterior weight. And so once we truncate G, so it never gets smaller than some critical threshold, well, then our denominator never gets smaller than some critical threshold. And hence, we never have a higher weight than something. So we can place an upper limit on the variance of this estimator as a function of many samples. The problem is now we've sampled from only a subset of the distribution. And so to get back what we want, we have to know what fraction of the posterior was contained within the volume that we truncated our importance sampling density to. And so we use the MCMC simulation to estimate what fraction of our posterior fell within the region where we truncate the importance sampling density. So here we have, repeating the last line, the truncated importance sampling density. If anyone's looking for a fun little project, this is actually a special case of that the ratio estimator I mentioned, where we've chosen for H, this is here, a top hat. It's 1 some places and 0 others. That's obviously a very simple choice. And if anyone's interested, perhaps they could explore some better choices for this H distribution, the numerator and denominator of what we affectionately call Jim's ratio estimator, to make an estimator for a marginalized likelihood generated from a posterior sample, and then samples drawn from an alternative distribution H. So we have 2 samples. One's the posterior from MCMC, one from H. This might need to be long because our MCMC might have correlations. The samples from H will be uncorrelated because it's an importance sampling density. So this can be much shorter. So your runtime is still limited by the MCMC, but now we can construct out an importance sampling estimate of the marginalized likelihood. So as I mentioned, we literally just chose the simplest thing, a top hat, in order to make some progress as astronomers, but there may be better properties if people chose more wisely. So that might be a fun idea for a project. How does this work in practice? Here's sort of the cartoon version where I have my target distribution in blue. It's a little bit funky. It's sort of just got a little bump over here. And I say, well, maybe I could approximate that pretty well with a Gaussian distribution G. So I'll make a little importance sampler where I draw from the Gaussian distribution to calculate the ratio of the red to the blue and add those up. And so that's the traditional marginalized likelihood for importance sampling. And the truncated version goes like this, basically the same thing, but now I truncate my density so that I never get out in the far tails, I never get a small denominator, but I don't know necessarily what the fraction of my posterior is contained within that range. And so that's why I then have to combine it with the fraction of the posterior falling within that range. So we've done this for cases of 3 and 4 planets, so dimensions of about 30. 3 planets, it worked pretty reliably. We didn't have to tune much. So at 15, 20-ish dimensions, it was working pretty well. When we went to that 4th planet, we sort of had to run things for a month on a GPU and convince ourselves that we believed our results. So around sort of 30-ish dimensions, this starts to become scarily inefficient, but perhaps not totally impractical, and hence my interest in finding ways to make it more efficient.
I noticed you mentioned Martin Weinberg's paper on the previous slide. So have you compared it with what?
No, I haven't compared his, but there's a...
So he's doing like the reciprocal of the likelihood thing, but truncating it like that?
He makes like a tree of local approximations, and so it's quite different than what he was doing, but it's sort of related. So
yeah, it involves some kind of truncation. That's what's similar.
Right. So it's making local approximations by truncating and using that to make a good importance sampling density.
I just didn't know anybody who used it but him.
I didn't actually. It was very complicated. Well, he used a very mathematical language that made it sort of hard to understand. But I think at the end of the day, it wasn't that tricky. But it didn't have a nice public code where you could just try it, so I didn't.
Martin Weinberg's an astronomer, but the paper was published in Bayesian Analysis, so it was vetted by statisticians.
But he does have a public code, but I don't think anybody uses it.
But it's for it's like specialized for galactic structure.
I mean, it's a huge, monstrous,
A very big framework.
It might be useful with some LSST or Gaia thing in the future, I don't know. But so perhaps the most interesting case we apply this to is the GJ876 system. So we mentioned this previously. This is the one that spins around once every 9 years, the orbits of these two giant planets. It's the reason the interactions are so fast is we have giant planets that are in a low mass star. And so the planet-star mass ratio is not as extreme as in most planetary systems. And so we have these two strongly interacting planets, then also a super Earth close in. And then this planet here was debated. So someone had proposed maybe there's a fourth planet further out. And it's interesting because you notice these two planets have orbital periods of nearly 30 and 60 days. That looks like a ratio of 2 to 1. Remember, we got excited about this is proof of there's orbital migration and sort of proving a whole branch of planet formation theory. And then this one was at just 120 days. And if that's true, well then that changes everything, because now not just did 2 planets get trapped in resonance, but you had a third one that sort of came in and didn't disrupt, and that's really, mass is very different, and so the migration rates. So the theorists really get excited about this, but they're like, but the data's kind of crummy. I don't know if I believe it, so if I don't like the results, I just say I'll ignore it. And so we wanted to ask the question, what's the actual evidence for this planet? Also, it doesn't help that this, well, so besides the issue of harmonics, that this star has some stellar activity as well. And so there's concern about could the stellar activity be sort of confused with an additional planet. So we use this restricted importance sampling method to calculate the marginalized likelihoods or evidences comparing various pairs of models at a time. So Ben, the graduate student, did this, sort of viewed it as a series of bouts. And so the first thing we did was said, well, imagine there were just 3 planets. Should we use the inner 3 or the outer 3? The first 2 were really obvious, so there's no question those first 2 signals are there. But that inner planet, that required really subtracting the first 2 planet signal to find it. The outer one also is pretty small. Maybe we should have first added the outer planet before looking for the inner one. The inner one would go away. But it was clear that the inner planet actually, there was much stronger evidence than for the outer planet. And next we sort of did a comparison. Well, what if we took those 3 planets, and then we added just a sinusoid that was constrained to be near 120 days. And there's strong evidence that there's a sinusoid in the data beyond just a 3-planet model. So clearly there's something more than just those 3 planets. And then we asked, well, what if we put in a 4-planet model where planets are interacting, they're roughly Keplerian orbits, but they're precessing, and that changes things. And we compare that model to just 3 interacting planets and an arbitrary sinusoid. And here we get that, well, the planetary model is favored, but only favored by a factor of 30. Now, if I really believed all this stuff, I would say, oh, a factor of 30. That means there's a 97% chance that there's 4 planets compared to 3 planets in a sinusoid, and maybe I'd take that pretty seriously. My experience is that base factors of 30 are not necessarily telling you that there's, I have to keep in the back of my head that I have a mathematical model that's only approximation of reality. There's some stellar activity going on. It's probably not really exactly a sinusoid.
Plus the priors that you had to put on the parameters aren't really the population distribution.
Right, I actually don't think the prior is that big of a deal, but I think my likelihood is the bigger issue. I assume Gaussian residuals and uncorrelated, and so with all of the assumptions there, do I really want to be 100% confident this 4th planet versus 3 planets in a sinusoid? Probably not. As an astronomer, I might say, well, what would cause a 120-day sinusoid? The rotation of the period of the star is much less, and so most activity signals should be significantly lower. So on one hand, there's evidence for some signal at 120 days, and it seems astronomically that that's most likely to be a planet. But from a purely statistician's point of view, it's not conclusively shown that it must be a planet. So we'll call that a marginal victory for the planet case. If we condition on the 4-planet model and say let 4th planet's there, then we can go about trying to measure things. So we can basically ask the question, when we make these 4-planet models, are we actually seeing planet interactions, or are we sort of just choosing something that happens with the data a little better because we made it a little bit non-circular, a little bit add a second harmonic, but it's not really interacting. And so what we can see here is that when we put in that fourth planet, and then we take posterior samples and we evolve them forward, there are specific combinations of the directions in which the orbit are pointed that track each other. So we had known that the two massive planets, their orbits, remember, were spinning right every 9 years, and they were tracking each other to within 10, 20 degrees. But then the interesting thing is, there's another angle that's related to the 3 planets that have this ratio of 1 to 4, similar to the Galilean moons, Io, Europa, and Ganymede. And we can look at the amplitude of that angle, and we can see that that angle also has an amplitude, well, arguably, if you assume they're coplanar, say 20 to 50 degrees. If you assume isotropic priors, then maybe 40 to 60 degrees. But nevertheless, if this had just been randomly fitting some sinusoid of the data, we wouldn't be finding orbital models that favored a small libration amplitude about a Laplace resonance. And so based on that, we're sort of fairly confident this fourth planet is here through the extending the analysis from just statistics to bringing in the seeing that the physics of the models we find is under sort of special properties that a priori would be unlikely. So that's perhaps our most advanced application, 2 advanced applications of Bayesian analyses to the exoplanet observations with radial velocities of multiple planet systems. Each of those is multiple weeks, almost a month of GPU time. Maybe with a day's GPU, it would only be a week, because at the time it was old GPUs. But nevertheless, they're pretty computationally intensive. And so that's roughly where the state of the art is. But I want to say a little bit about where the future is going. So I've alluded several times. So far, we've basically ignored the stellar activity, or we've said the stellar activity causes a random perturbation that's uncorrelated from one observation to the next. And what we now are encountering is that oftentimes the activity is significant. The other thing is, in the old days, people might look at 100 stars, and they might pick the 50 that seem to be the best behaved of those 100. And they'd observe them some more. And they'd pick the 20 of those that seem to be the best behaved. And then of those, they'd pick the 10 best, and they'd observe those 10 a whole lot. And then by design, those 10 stars don't have much activity because we've picked them that way. In the future, we're going to do things like find a planet that has extra exciting properties, like it passes in front of its stars, so we can measure its size and perhaps try to study its atmosphere, and then say we'd like to go measure the mass of that planet. Well, in that case, you can't be so picky, right? Because now nature's picking the ones that you want to observe, rather than you getting to pick the star and then selecting the most favorable stars. And so as we have surveys that have to deal with the wider properties of the stars, dealing with stellar activity becomes more important. So maybe a little bit of showing how this manifests itself in practice. You can sort of imagine the solar disk as being a bunch of spectra, and each spectrum is weighted by the fact that the center light is coming straight towards you, like straight out of the sun. But the edges are going through more of the star's atmosphere. So they're limb darkened, not as bright. And the side that's rotating towards you is shifted to the left, and the side that's rotating away from you is shifted to the right. And so we have these different lines with different intensities and shifts being added together and giving you one integrated spectrum. But then if instead of having a nice smoothly varying surface intensity, you have little spots over here, well, now there's these variations that block some of the light that normally would be receding away from you. And so it doesn't now nicely cancel the sort of corresponding patch of disk on the other side. And so this spot here doesn't cancel that one. And so we have changes in the spectrum that are due to this stellar activity. And the annoying thing is that that can sometimes look like a Doppler shift, particularly the way that codes were designed. In the old days, they assumed that these sorts of changes weren't happening. And so now we're trying to develop ways to recognize those changes. In principle, the shapes of the lines change and there's information there, but that's sort of an area of active research. And so as we begin to search for radial velocity evidence of planets around active stars, we need to have lots of observations so that we can have high enough quality data sets. We also need to be able to develop a model for stellar activity. So instead of having it's Newton's laws of gravity, this is a perfectly well characterized model. There's hardly any uncertainty at all. It's a matter of estimating parameters. Now we have a complex physical process that we can't don't really understand. We require 3D MHD simulations that take forever. And so we need to be able to at least characterize statistically the properties of that noise. So it takes a lot of observations. Also, the process I described was we took every one of those spectrum, those nice, big, pretty pictures, and we said I'm going to take that 4 million pixel data set, and I'm going to reduce it to 2 numbers, the velocity and the uncertainty. And sort of each image got translated to a y value and an error bar. And so now we need ways to look for extra information, not just that one piece of information of the Doppler shift, but other indicators that can help us recognize activity. And then, of course, we need a way to do this in a statistically valid way. And so that's what the team Davids is working on. And why do we need to do this? And this is sort of going back to the philosophy, and that is people have started making extraordinary claims, such as we found an Earth mass planet around Alpha Cen b, the nearest star system to us. And so well-known, well-respected astronomy groups published this discovery. At the time, I remember, thinking, I don't believe this. It was like, weak statistically. But what can I do? I don't want to spend my time writing a paper saying, I think your statistics isn't so great. I'm not sure I believe your planet. So I just kind of sit back and wait. Of course, things like this can get a lot of publicity. Well, several years later, someone else comes by and analyze, say, I look at the same data set, and that planet doesn't exist. And for a while, it sort of, one paper, 2 paper, and there's a little bit of back and forth. At this point, the sort of lead author of the original study has basically conceded, yeah, I think the evidence is now strong enough that sort of realizes that the evidence for the planet wasn't really there. So this is an example of the need to bring responsible statistics to exoplanet discovery. It's where we push the limits of finding planets, both because we're pushing the limits of the technology and also because we're doing things that occasionally get publicity and the public's attention. And so what I like to think of is there's a lot of issues where science we'd like to think would inform decisions in society. And sometimes it's complicated. There's political and economic implications if we make one choice or the other, and there's kind of incentives for people doing stuff to maybe, in this case, it's cool, we gotta know, but there's really no, if we can't get it right, whether or not there's a planet that has no economic impact on anybody, no one's gonna change their politics over this planet. If scientists can't get that right, how can the public trust people making claims that sort of say, because of my analysis of your data, I want you to stop doing something that is how you make your living, right? So there's sort of an element of the purity of astronomy as a science. The willingness of us to share our data and cross-check each other, I think, is a feature. And we could be a sort of beacon for the scientific process and how science can get things right. I'm not sure we're there yet, so we still have a little ways to go, but I'd like to see that. And I'll see, how are we doing on time? Because I could go in a couple of different directions now.
Nominally you have 9 minutes.
Okay.
You have 9 minutes.
9 minutes is about the right time to answer some questions. So I perhaps talked too much the second segment. So maybe I'll pause and try to stimulate a few questions. John. Oh, let's see. Good pick right. John.
I don't have any questions from here. The 2 different MCMC methods we hadn't heard of before. So
Okay.
I'm gonna look into that.
Yeah, as Eric mentioned, they get a fair bit of use in astronomy, and at least they have been used in other fields, but I don't think that often. And so there may actually be some cases where it's valuable in other fields, and we sort of bumbled into finding it, or perhaps there's lessons in other fields that we should bring back to Exoplanet. So be good to see compare, like David mentioned over the break, comparing it to adaptive Markov chain Monte Carlo methods, and I haven't actually tried that, so I don't know how they compare objectively. Okay, Yasser.
Yep.
Your best question. You actually had a good one over the break, so I look for another one.
Do you want me to come back to that?
Well, I'm inspired by, you had a great question on the break, maybe you another one now.
Okay. One thing is that I'm looking at the graphs is on velocity observations on each time point. How do you observe different velocity on given point?
So,
I may miss something, but
well, I went over things quickly, so it's totally understandable that sometimes after hearing a bunch of other stuff, it sort of have to remind yourself of where this all started from. So each observation, we've taken the starlight and broken up across wavelength across our detector like this. And so each line here is the star's light spread out over many wavelengths. And there's all these little lines. And the ones you see are actually the big ones. There's lots more thin ones you can't tell. And so from these, we then look for the shift of the Doppler effect and measure that shift. And the magnitude of that shift is what we're reporting as the y-axis, the velocity of the star. And so the way astronomers have done this traditionally is they've taken two spectra of the star and they've slid them back and forth until they basically lined up. Oh, maybe I should have done this way. It's just a handedness issue. And they say, oh, how much can I slide it back and forth these two things line up? The good thing about this is that you don't actually have to have the perfect stellar model, right? Because you're sort of comparing something to itself at another time and finding where it agrees. The bad thing is this is combining data in a way that doesn't really have the right weights in some sense. And so one of the things we're working on now is coming up with better ways to extract this velocity so as to perhaps try to make use of more different wavelengths that currently aren't being used as efficiently as they could. It's complicated by real life effects, like there's an atmosphere we have to look through that has water in it. Obviously good for many parts of life, but annoying for astronomers. And so dealing with that contamination from water lines, and traditionally astronomers kind of say, oh, all this stuff up here, it's kind of useless. Just block out entire sections of it because the water is so annoying. But there's actually good information in there. But as you get pickier and pickier, you can find small little water lines. And so another one of the working groups in this program is trying to develop methods to extract those velocities with more precision.
It's probably important to emphasize the difficulty of this, that the shifts that Eric's talking about are tiny fractions of the widths of these lines.
Yeah, so one line, so the star's rotating at several, if not 10 kilometers per second. So you have part of the sunlight, it's coming towards you at, say, 5 kilometers per second. Part of it's going away from you at 5 kilometers. And that's causing the line to not be a spike, but rather a broad, basically Gaussian profile. We're looking for that whole thing to shift by, say, a meter per second, so 1/1000th of the line width. If I try to do that on one line, I'm not going to notice. The only way they're able to pull this off is by combining information across a large chunk of the spectrum, or at least many different wavelengths, many lines, thousands of lines, to recognize the shift in these lines. But that also means because they're trying to pull out such a small signal, that little annoying effects like spots or water contamination can sometimes masquerade or sort of imitate that effect. And so that's why we're trying to be more careful about how to extract those velocities. Suman.
So I have a simple question, but I think probably you do it. I mean, often. So what happens whenever a planet is orbiting around a star? So there is a physical equation of that rotation, right? Mm-hmm. So can we translate that equation to how it will affect the lights coming from the star, and perhaps like match whether the data actually complies with that physical equation? I mean, without using the direct time series, when you have some like physical knowledge about like how the star rotates and how the light should get affected.
I'm not sure I understood exactly. So my first answer was going to be, that's exactly what we're doing. We're comparing the prediction of the path of the planet, effect of the path of the star, and then the path of the star is what we're comparing to a model. But then maybe you said something, maybe that wasn't what you were asking. Maybe you were asking...
I'm talking about physical models, like say a velocity model, Newtonian model.
Right.
So are we comparing that with that kind of model, or say a time series model? That's a statistical model, not really a physical model.
Well, so we're comparing the time series predicted by Newton's laws of motion with the time series of velocities extracted from this set of spectra. So at each time we have one of these spectra, and the traditional thing to do is to reduce it to a velocity, and that velocity is being compared to the physical model.
Okay. So it's a parametric time series model, but it's a physical, it's a deterministic physical parametric model.
So one of the things that sometimes makes astrophysics different than some other fields is that oftentimes our goal is to gain intuition to physics, right? So we want there to be a model that describes the universe that we can learn about that model. And in some cases, the model's really, really good. So if we have a 30 meter per second signal around a quiet star, the motion can basically be described by Kepler's laws of motion, and we have a great physical model, so we can basically do parameter inference on that model. In other cases, if I go to something like, well, I want to know what the distribution of planetary systems in the universe is, well, now that I don't have I might have a collection of theoretical models, each of which I could maybe in principle make predictions, but I don't believe any of them. And so I sort of want to do something much more akin to sort of, not naive, but like a non-parametric or semi-parametric model that puts in relatively little assumptions. I just want to characterize what's the distribution of orbital periods or orbital mass, or planet masses, and maybe look, are they correlated with each other? And so there are some questions where we act, I sort of say, like social scientists, trying to make a very oversimplified model of the universe. And there are some situations where we act like physicists, where we say, nature follows these laws, we want to measure this one parameter. And one of the challenges as we shift towards smaller planets is we're kind of getting in a combination where the planets are obeying a set of physical laws and we want to measure their masses and orbits, but the star is a big complicated mess, and we kind of want a model that's good enough that we can understand the implications of the star not being a perfect light bulb and sort of marginalize over them, right? We're not actually trying to see what the spot is at any exact period of time, but we want to understand the star well enough that we can do good inference on the properties of the planets.
This is one of the things that drew me, I work in this field too, that drew me to it about 15 years ago or so, was I like doing parametric inference. And this is one of the few places in science where, for larger planets, where we have a parametric model you can write down in a line or two that just is a really accurate description of the system. 5 parameters, which is like it's one transcendental equation and one other equation, and there's really nothing else there that you really expect it to follow that to high accuracy, as long as there aren't other planets nearby. So it was a really nice problem for parametric statistics where the model is actually not misspecified. Right. It's really, there aren't a lot of problems.
Even when there is another planet nearby, then also the interaction between the planets can be measured by physics, right?
Yeah, so then you need to do this n-body calculation.
So instead of being sort of 2 equations, now it becomes solving a differential equation. So it's significantly more computationally costly, but from a statistician's point of view, it's just changing the black box for the black with blue stripes box, and takes 1,000 times longer, but it's just as good, basically. I think that's basically time, so I can stick around a little while if people want to ask questions further. And I guess next week, Becky Dawson will talk about exoplanet time series, but instead of radial velocities, we'll talk about other planet detection methods and focus on some of those that have different types of challenges. So.
Thank you very much, Eric. That was really exciting.